All right, guys. So last video today with the electricity review. So the last unit, last review before you do your test. So if you want to check this out, you should. Um, again, I skipped the vocab because I figured you can get that. First problem says an object has an excess charge of positive 6 times 10 to the negative 6 coulombs. It's placed 1.2 meters away from another object that has a charge of negative 4.3 times 10 to the negative 6 coulombs. So part A, we're trying to find the size of the electrical force, so just the number that goes along with that. So it's just plugging into Coulomb's law, which is that Fe equals K Q1 Q2 divided by R squared. So if you plug those numbers in the same way I did, you should get 0.16125 newtons. That's the answer to part A. So part B is the same question, really. It's just saying, okay, how's that going to affect the negative? It's the same because it's an action-reaction pair. So in that simulation that you guys did with Coulomb's law, you should have saw that the force on each of those charges, regardless if it was positive or negative, was the same amount or number, but just oppositely directed. Part C wants to know describe the force of interaction. So is it attractive? Is it repulsive? It's going to be attractive, and that's because they're oppositely charged. So you have a positive and a negative, so they're going to try to attract each other. For some reason, I had D skipped, so we just go to E, and E says if what would happen if the sign of one of the charges was changed. So if it changed from positive to negative or negative to positive, the two charges would become the same type of charge. So they would be alike, and because they're alike, they repel. F and G are asking about what's going to happen to the amount of force or the size of the force if the charges were reduced. So if the numbers got smaller here in Q, and if the numbers get smaller, then the force gets smaller because less charge means less force. And then finally, the distance, if the distance was going to get bigger, so you spread the charges out more, then the R value should increase, or R value increases and then the force decreases. So that's the first problem. So hopefully that was good for that one. Second one, I didn't have a block up, but that's okay. So you got two charges, 80 and negative 14, and you want to know their net charge, so it's just adding. So 80 plus negative 14 gets you positive 66. If they're touched and then separated, what charge would they end up with? So you just divide that 66 by 2 and you get 33. And the reason why this happens is the charges just keep moving and trying to balance out or reach equilibrium, and they continue to do that until they reach equilibrium. So to get the total charge on each one, you just take to get the charge on each one, you just take the total charge and divide it by 2. All right, so then the last two problems are on circuits. First one, this is a series circuit, so you got 100-volt battery connected to 3 resistors, 15 ohms, 2 ohms, and 25 ohms. And you're supposed to find the equivalent. Equivalent just means total. So, sorry, I used an old term. So it's the total, because I'm old, the total resistance. So the total resistance, you just add them together, and it'd be 15 plus 25 plus 2, and that's 42 ohms. Then you're supposed to calculate the current, voltage, and power for each one. So the first thing I do is try to figure out, okay, how much current goes through this whole resistor or circuit. The current that goes through A is also the current that goes through B, and this is the current that goes through C. So I'm just going to use Ohm's law. So Ohm's law, 100 volts for the total voltage equals the total current times the total resistance, which you just found to be 42. So if you divide 100 by 42, you get 2.38. It's rounded a little bit, but it's close enough. And then I just mentioned like the current that leaves the battery is the current that goes through everything. So that's all 2.8 or 2.38, excuse me. Once you know that and you know their individual resistances, to solve for the voltages is pretty easy. It's again just using Ohm's law with whatever individual resistor you have. So 2.38 is the current for A, and the 15 ohms is the resistance of A. So when you multiply those together, you get 35.7. Similar work for B and C, just switching out the resistances and then multiplying it by the currents. Then to do the power, you're just going to use PIV, so P equals IV, and again, you're just going to use the individual current and the individual voltage for each one. So when you do that, get out of here. Maybe not. Let's just do that. Then you should take that current, which is still 2.38 for each one, and multiply it by the answers you just got here for the voltages. So 2.38 times 35.7 gets you somewhere close to 85. I think I rounded that one. And then you get different values, as you can see, because of those different voltages. If you wanted to check it, you could do the total current times the total voltage, which is 2.38 times 100, so that'd be 238. And if you add those together, so you get something really close to 238, just to check. Finally, the last one here with the circuits, again, equivalent isn't the best. I don't use that terminology anymore, so it's total resistance. But in this one, it's a parallel setup, so you got to do the parallel rule. So the parallel rule is the inverse, add, and then inverse again. So it'd be 1 over 5 plus 1 over 15 plus 1 over 30, and all that to the -1. I just label them A, B, and C to be able to talk about them easier and refer to them as that. So this turns out to be 10 over 3 or 3.33 ohms. This is repeating, but I don't write out all the digits, so we'll just go with that. Next idea is that the total voltage in a parallel circuit is equal to the voltage across each piece, because we talked about that loop rule. So whatever you gain across the battery is what you're going to drop across each individual path. So each one of these is 15 volts. And then we know the voltage and we know the resistance. So again, solving for the current isn't too much trouble. It's a little bit different math than we did on the last problem, but it's just, you know V, you know R, you're looking for I. So 15 divided by 5 will get you IA, which is 3. 15 divided by 15 will get you 1 amp, which is IB. And then for IC, it'd be 15 divided by 30, which is 0.5. Also, this makes sense that, you know, the less current is going to go through the resistor that is larger, and more current is going to go through the resistor that is smaller, and that follows the rule that we talked about. If you wanted to find the total current, you would just add these up, so that's 4.5. And if you wanted to check, you know the total resistance and you know the total voltage. So if you do 15 divided by, so 15 is the total voltage. Total current is what we're going to look for, so I'll just label that IT. And then total resistance, I'm going to use 10/3 because the math works out exactly right if you do that. If you use 3.33, you round it a little bit. But if I'm solving for the total current here, I would just take this 15 and divide it by 10/3. And that turns out to be 4.5. So, and that's 4.5 amps. So that is a check that you can do to make sure you did these right. Then the power equation, again, it's just P equals IV. I'm going to get rid of that thing. So P equals IV, so for each one, you just take the individual current times the voltage. They're all 15, and you could figure that out here for each one of these. So the individual voltages, if you add them all up, it should get you the total power, so the total current times the total voltage, so 4.5 times 15 gets you the sum of that, which is 67.5. So that all works out and checks out and hopefully makes sense to you, even though I went through that really fast. So that is the last of the videos that I got for you. So hopefully this has been helpful. I'm sorry that we didn't get to meet more in person. I did really enjoy our class, and we were having some fun with the labs, and hopefully you were learning some, but hopefully this worked out okay. And again, just make sure you're checking in with me, you're emailing, or to let me know if you have any questions or concerns. So best of luck, guys, in your future, and be safe and be well.